Okay, so today we're going to look at boiling and condensing. So we're going to specifically zero in on this change of state. What I have here is a picture of a distillation apparatus. If you've ever seen a show like Moonshiners on TV, what they're doing is they're distilling alcohol. And how they do that is they use the boiling points of different substances to separate them. And this is how we can have distilled water. It's the same idea. So let's say you have some salt water that you want to purify. We can heat the salt water, and once we know the water, the temperature of that vapor here, as the vapor rises up, once we know the temperature of that vapor is 100 degrees Celsius, we know that that is the water boiling. So any vapor molecules rising at 100 degrees Celsius, then we know that's water, and the vapor will come down, gets trapped in here, comes down this tube, and as it's going through this tube, we run cooling water to cool down that vapor, and then it turns back to liquid, and it drops out here. You get a distillate, and that's your pure water. And it'll leave the salt behind because salt does not boil till well past 100 degrees. So this is a way that we can actually separate and purify liquids, which is really all that they're doing when they're making moonshine. They're just purifying alcohol. So factors affecting changes of state. So what will affect the temperatures that things melt or boil at? So the first thing is the intermolecular forces, and that's probably the biggest one, is remember, in order to melt or boil, you have to overcome those intermolecular forces. So high melting points and boiling points usually mean that there are strong intermolecular forces. The other one is how big these molecules are. Typically, larger molecules will take more energy to move, so in order to get them moving, you have to apply more heat, so their boiling points and melting points will typically be a little bit higher. Heavier molecules have high melting points and boiling points. Ionic versus covalent, so we're talking again kind of more about intermolecular forces, kind of the way they're held together. Again, you're going to have stronger forces with ionic compounds, so they're a little bit more ordered and structured. Polar compounds, now we're going to focus on polar compounds a little bit more when we get to solutions. But again, polar compounds will have stronger IMFs, so again, it's really mostly about the intermolecular forces. But using these factors, we can rank compounds in terms of like their boiling points and determine what they might be based on how big the molecules are or the types of bonds or forces they have between them. Remember that boiling happens anytime the molecules of a liquid get enough energy to overcome the force of the pressure of our atmosphere. So this is kind of the big important part, and we're going to focus in on how vapor pressure and atmospheric pressure have to be related in the next lesson. But pressure is a huge factor. So this is why you can boil water at room temperature, because you can remove the pressure of the atmosphere that holds that water in the liquid phase. The higher the pressure of the atmosphere, the higher the boiling point, since it's more difficult for those molecules to escape. So this is the idea behind a pressure cooker. You pressurize the hot boiling water, and it makes it boil at a temperature hotter than 100 degrees Celsius. So it's because it's harder for the molecules to escape. So here's a couple of examples of that. Water in a vacuum, not a vacuum cleaner, but like a vacuum where there's no atmosphere, will boil at room temperature. Water at 1 atmosphere boils at 100 degrees. If you put water under pressure, though, at 3 atmospheres, it boils way higher than 100 degrees. So these are all the different factors that can affect your boiling points and sometimes your melting and freezing points as well.